Good day everyone. We are the Group 1 and today we are going to tackle about simple stresses, tolerance and allowances, variance stress, and the materials and their properties. So, ano nga ba ang mga ito? So first, we have simple stresses. It refers to the basic types of internal resistance that materials experience when subjected to external forces. So dito, ang pag-iintindi sa stresses ay mahalaga sa ating mga engineers at sa ating mga designers para malaman nila kung paano mag-behave ang isang material under the load at upang maiwasan ang premature failure, deformation, or structural collapse. We have the formula: stress is equals to force all over area, where stress sigma is defined as the internal force per unit area. Sigma, yung ating stress measured in pascals, PSI or Newton meter squared. Sa force natin is yung force natin in Newton, area is the cross-sectional area in square meters. So kapag mataas ang force o maliit ang area kung saan na-apply ang force, mas mataas ang stress. Kaya mahalaga sa design na mapili ang tamang material na gagamitin natin para mabawasan yung ating mga stresses. So we have the types of stresses: the tensile stress, compressive stress, and the last one is the shear stress. So ano nga ba ang mga ito? Tensile stress. Ito ay nangyayari kapag ang material natin ay hinahatak o ini-stretch. Ito ay dulot ng force na nagtutulak palabas mula sa dalawang magkabilang dulo. So, dito, yung ating mga molecules is hinihila papalayo sa isa't isa. Kumbaga, kapag lumampas ang force sa limit ng material, maaari itong magresulta sa fracture o pagkaputol. Halimbawa na lang dito is yung ating mga ropes or cables. Isipin mo ang lubid kapag ginagamit natin sa towing o sa suspension bridges. Kapag hinihila ito magkabilang dulo, yung lubid ay nakaka-experience ng tensile stress. Kumbaga hinahatak siya. At pwede rin ito sa ating mga metal sa mga laboratory test. Ang metal bars ay hinihila upang masukat ang kanilang tensile strength at makita kung gaano kalakas ito bago masira. So, ang formula din natin dito is the sigma is equals to force all over area pa rin. Dito po yung ating force ay yung ating pulling force na nagdudulot sa ating tensile stress or yung ating stretching. Sa area po is ganun pa rin measured in square meter. Pangalawa po is yung ating compressive stress. Compressive stress occurs when forces act to compress or shorten a material. The material experience a pushing force. Dito sa compressive stress, nangyayari po ito kapag ang material natin ay pinipiga o pinapalit dahil sa applied force natin. Yung force po natin ay nagtutulak papasok sa material. So, kapag po nasobrahan yung ating compressive stress, yung mga ito po ay maaaring magresulta sa buckling lalo na sa mga slender structures natin o crashing kung napasobra po yung ating load. So, katulad po ng ating mga building columns o mga haligi, yung pillars, dito po yung mga columns ng mga buildings natin o gusali ay madalas nakakaranas ng compressive stress mula sa weight ng mga palapag na nasa itaas. Kasi iba pa dito is yung ating mga concrete blocks. Ito po ay yung mga foundation walls at pillars. Yung concrete po nito ay kailangan na ma-design para ma-resist ang compressive force natin upang hindi po agad ito mabasag. Ang formula po natin dito is same pa rin. Sigma is equals to force all over area. Ang force po natin dito ay yung pushing or squeezing force na nagdudulot ng ating compression. The last one is the shear stress. Dito sa shear stress, nangyayari po dito is yung parang pinupunit siya. Inilalapat ng parallel na naging sanhi ng pag-slide o pagkapunit ng ating materials. Sa internal behavior po nito is yung mga particle ng material natin ay hinahatak palayo. Sa halip ay ito po ay nag-i-slide o nagsisip sa magkabilang direction, kaya ito ay napupunit. Excessive shear stress ay pwedeng magdulot ng cracks o separation sa interfaces ng material at mahalaga na lalo ito sa ating mga bolted or riveted joints. Example po dito is yung ating mga bolted joints. Sa mga machines o structural assembles, kapag may sideway force, ang bolts ay nakakaranas ng shear stress. Ito ay mahalaga sa design ng connection para maiwasan ng loosening o failure. Sa gunting, ganun din po sa gunting. Kapag nagugupit po tayo ng papel, yung blade po ng gunting natin nag-apply ng shear force na nagiging sanhi po para yung ating papel ay magunting. Formula po natin dito is same pa din. Force all over area din. Yung symbol po ng shear stress natin which is yung ating tau. Ang force po natin dito ay yung nagdudulot po ng sliding o pagkapunit. So ang unit po ng stress natin ay ginagamit po natin dito is madalas is pascals or yung ating PSI, pwede ring megapascals. At sa stress distribution po, hindi laging uniform ang stress distribution sa isang material. Halimbawa na lang sa isang beam na naka-apply ng bending moment, ang tensile at compressive stress ay magbabago depende sa layo o mula sa neutral axis. Ang kasama dito sa stress na malaman din natin which is the deformation or change in shape relative to the dimensions. So, ang material behavior po natin sa tensile is kapag po yung tensile stress natin ay sobra, maaaring magresulta ito sa neckling o pagkakaroon ng fracture sa material. Sa compressive po, kapag sobra, ay maaaring mag-collapse, lalo na kung hindi po ito suportado ng maayos katulad po ng mga buckling sa mga cylinder columns po natin. Sa shear failure po naman is maaaring magkaroon ng sliding at separation ng layers na madalas makita sa ating mga structural joints o sa fracture surfaces. So, bilang mga engineer po, ginagamitan po natin ito ng safety factors kapag dinedesign yung structures para masigurado po natin na kahit pa may mga stress concentrations o unexpected loads, hindi agad maaabot ang failure point ng ating mga materials. At meron din po tayong mga material testing katulad po ng tensile test, compression test, at shear test to help determine the ultimate strength of the material and predict how it will behave under various stress conditions. So, meron po tayo ditong sample problem. A tensile load of 60 kN is gradually applied to a circular bar of 4 cm diameter and 5 meter long. If the value of E elasticity is equals to 2 times 10 raised to 2 Newton per square millimeter, determine stretch in the rod, stresses in the rod, and strain energy absorbed by the rod. So, dito, meron po tayong given na load which is yung ating 60 kN. Tapos po meron tayong circular bar na may diameter na 4 cm at may habang 5 meter. At elasticity na 2 times 10 raised to 2 Newton square millimeter. Balang gagawin lang po natin dito is i-convert muna natin yung kilonewton to Newton. So, 60 kilonewton times 1,000 is equals to 60,000 Newton. The diameter po natin is 4 cm to millimeter is 4 times 10 is equals to 40 millimeter. At sa length po natin na 5 meter, gagawin nating millimeter din, is 5 meter times 1,000 is equals to 5,000 millimeter. So, same pa rin naman po yung ating formula katulad po ng mga nabanggit ko kanina. So, stress is equals to force all over area. Bali, direct substitution lang po ito. Sa force natin is 60,000 Newton divide 400 pi. Ang area po natin, kaya naging 400 pi is, area is equals to pi d squared all over 4. Bale, magiging sagot po natin dito is 400 pi millimeter squared. So kapag direct substitute po natin yung 60,000 Newton divide 400 pi, magiging sagot po natin sa ating stretch deformation is 47.746 Newton per square millimeter. So, next problem po natin is determine the compression stress of a column shown if it carries a load of 150 kN. Dito, may given po tayo na 150 kN compression stress. Tapos, sa ating diameter naman is meron tayong outside diameter at inside diameter. Sa outside diameter natin is meron tayong 175 mm at sa inside ay 125 mm. Bali gagawin lang po natin dito is yung kilonewton to newton ulit. So 150 kilonewton is equals to 150,000 newton. Sa area naman natin is okay na, hindi na natin kailangan. So kumbaga kukuhain muna natin yung ating area. So area is equals to pi over 4 outside diameter squared minus pi over 4 inside diameter squared. Sasubstitute lang natin to. Area is equals to pi over 4 times outside diameter na 175 squared minus pi over 4 125 mm squared is equals to 11,780.97 square millimeter. So ang formula po natin sa compression is sigma is equals to force all over area. Isa-substitute lang natin yung force natin na 150,000 Newton divide sa nakuha nating area na 11,780.97 square millimeter. At magkakaroon po tayong sagot na 12.73 Newton per square millimeter o simply 12.73 megapascal. Last problem po natin para sa ating stress is a block of material is subjected to a shear stress of 250 kilopascal. If the material's modulus of rigidity, symbol po natin is G, is 50 megapascal, calculate the shear stress. So, hinahanap po natin dito yung ating shear stress. Sa shear stress natin is same formula pa din, force all over area. So, meron tayong shear stress na force na 250 kilopascal at rigidity na 50 megapascal. So, direct substitution lang po. Yung ating 250 kilopascal gagawin nating pascal by multiplying it to 1,000. So, 250,000 pascal divide 50 times 10 raised to 6 yung ating rigidity. At makukuha po natin yung sagot na 0.005 radians. And the next reporter po is si Joel Varias. Thank you.
Under simple stress is what we call tensile strength and yield strength. Tensile strength is the maximum amount of tensile stress that a material can withstand before failing or breaking. It is measures of material's ability to resist deformation and fracture under tension. Knowing that the tensile strength of a material helps engineering designs a component that can withstand an expected load without breaking. It is a crucial part for safety and for efficiency of a performance in structures like bridge, buildings, and vehicle. There are different definitions of tensile strength. First is the ultimate tensile strength, which defines as the maximum stress a material can withstand. Second is what we call breaking stress, which defines as the stress level at which a material actually fails. Next is yield strength. Yield strength is the amount of stress that a material can withstand without permanent deformation. Beyond this point, the material will undergo a plastic deformation. meaning that it will not return to its original shape when the load is removed. Yield strength is a critical factor in a engineering design, as it indicates the maximum load that can be applied to a material without causing a permanent deformation. Also, it helps to ensure that the structure will maintain their shape under normal operating conditions. In summary, both tensile strength and yield strength are crucial in material selection and structural design, with yield strength focusing on the onset of deformation, while the tensile strength addressing the overall capacity to withstand the force before failure. Next is what we call modulus of elasticity. It is also known as Young's modulus. It is a measure of a stiffness of a material. It represents how much a material will deform. It's either stretching or being compressed. When subjected to a given force, essentially, it is described it describes the relationship between stress and strain in the linear elastic region of the material's behavior. And the formula for getting the elasticity modulus of elasticity is strain over stress. Next is bending. Bending occurs when a force or a moment is applied to a material. Example is like a beam, causing it to deform or curve. This results in a distribution of compressive stress on one side of the material and tensile stress on the opposite side. The point in the material where there is no stress is what we call the neutral axis. Example of bending application is number one is beams and bridges. Bending is a primary consideration when designing beams, as they must support load without failing. Engineer must ensure the bending stress does not exceed the material strength. Second is Second is mechanical shafts. Shafts is a in rotating machinery such as motor and engine are often designed to resist bending stresses from from applied loads. Third is the what we call the frame and support. Frame of a machine. It is the frame of a machine or building experiencing bending when they carry heavy loads. Next is what we call torsion. Torsion refers to the twisting of a material or structural elements when a torque, or also known as rotational force, is being applied along its axis. This leads to shear stresses within the material, causing it to twist. The degree of twist depends on the applied torque and the shear materials property. Example of the application of torsion is first is on the drive shafts. In vehicle, the drive shaft transmit power from the engine to the wheel and be and is being subjected to torsion. Second is coupling and clutches. These components transmit rotational motion between shafts and must be designed to resist torsional force. Third is gears and turbines. Gears is in machinery and turbines experience torsional force as they transmit rotational power. And last is mechanical testing. Torsion testing is used to understand how a material or components will behave under twisting loads. This is essential for ensuring the rea- reliability of parts like shafts and rods in a rotating machineries. Next is shear stress. Shear strain. Shear strain is a measurement of how much a material deforms when subjected to a shear stress. It represents the angular displacement between two parallel planes in the material, typically caused by force that acts parallel to these planes. When a shear force is applied to a material, the layer of material slides over each other, leading to a deformation which is quantified as shear strain. Shear strain is represented by Y gamma and also is defined as the ratio of displacement of one layer of a material to displace between the layers. And the formula for shear strain is Y gamma is equal to change in displacement over height. Next is torque. Torque is a measures Torque is a measure of a rotational force applied to an object, causing it to rotate around an axis. It is the turning or twisting force that results from applying a force at a distance from the axis of rotation. Torque is a fundamental concept in mechanical engineering, and it is a critical in understanding how machine, vehicles, and mechanical system works. Torque is the product of applied force and the distance from the axis of rotation, often referred to as the lever arm or moment arm. Formula for torque is T is equal to F times R times sine theta. Next is what we call strength of material. Strength of material in engineering design is a crucial part for ensuring that the structure, machines, and components we build are safe, reliable, and functional under loads and conditions that they will face. Key reason why material strength is important in a engineering designs. Number one is preventive measures. Is for preventing failure. Material failure can occur when a material is subjected to a force beyond its strength limits, leading to cracking, breaking, or permanent deformation. Number two is for safety purposes. Top of the list is about human safety is the top of priority in design engineering. In engineering design, weak materials are materials or improper material choices can result in a accident or disasters, especially in a critical infrastructure like buildings, airplanes, or medical devices. Third is optimizing performance. Material strength is also linked to how well a component can perform its intended function without failure or excessive wear. Fourth is longevity and durability. Material degrades over time due to factors like fatigue, wear, and corrosion. Understanding material strength helps engineers to predict how long a component can last before it needs to be replaced or be repaired. And fifth, fifth reason is the cost efficiency. Choosing the right material strength helps engineers to avoid an a over engineering using an unnecessary strong material or under engineering which means using material that can't handle the loads. After the key reason of material strength, we will go to the factor of safety. Factor of safety, or also known as safety factor. It is a measure of how much a stronger system or a component in that is that is than it needs to be for unintended load or stress. It provides a safety margin to account for our certainties, such as a material deflects, unexpected load, or error in design calculation. Based on yield strength, the formula for factor of safety is yield strength of material over working stress. Note that the yield strength is the stress at which a material being deformed plastically. Second is working stress is the maximum stress expected in the material during a normal operations. Based on ultimate strength, it is the factor safety formula is equal to ultimate strength of material over working stress. Note that the ultimate strength is the maximum stress that a material can withstand before failing or being fractured. Se- And next is why we should always consider the safety factors in our design as an engineer. First reason is to prevent failure, to account for uncertainties in a material properties, manufacturing defects, and unexpected stress, reducing the risk of a catastrophic failure. Second is the account for a unpredictable loads. Design must be able to handle extreme or fluctuating loads that may go beyond the calculated values. Third reason is human error. Human error. Under the human error, safety factors can provide a margin for miscalculation, designs, design mistake, or variation in materials. Fourth reason is what we call is about fatigue and wears. Components experience gradual wears and fatigue. So safety factors ensures long-term durability under repeated loading. Compliance and regulation. Many industry require safety factors to meet the regularity standard and to ensure the public safety. And last is the cost and efficiency. They help balance safety with efficiency, avoiding over-engineering while ensuring reliability.
Let us now proceed to tolerances and allowances. So, since we are dealing with machine design, machines are made up of moving components in which these are interconnected parts moving together as one. With that being said, these parts cannot be loosely or tightly fitted. There can only be a perfect range of motion in order for it to properly work. These are called tolerances and allowances. Tolerances is the total amount that a specified dimension is permitted to vary. So this is the range of dimension that a part can be created, a variation in size. It is the difference between the maximum and the minimum limits for the dimension. So in order to get the value of tolerance, you need to subtract the maximum and minimum limits of the given dimension. For example, a dimension given as 1.625 positive negative 0.002 means that the manufactured part may be 1.627 or 1.623 or anywhere in between those limit dimensions. So in order to get our tolerance, we have to subtract 1.627 to 1.623. So there we can get our tolerance, which is 0.004. So next, types of tolerances. Unilateral tolerances when the two limit dimensions are only one side of the nominal size, either above or below. The tolerances are said to be unilateral. For unilateral tolerances, a case may occur when one of the limits coincide with the basic size. So, given the name unilateral, uni meaning one, so the tolerances only moves in one part of the limit, either above or below, only in one direction. In contrast, bilateral tolerances, when the two limit dimensions are above and below nominal size, on either side of the nominal size, the tolerances are said to be bilateral. So that means bilateral, both of the directions above and below, in which the dimension may vary. So here are some examples of dimensions. So here are just samples on how to compute for the tolerance. It's just subtraction. So next, specifications for tolerances. These are the ways for the units to be expressed. It could be either like this, in which the positive and negative values are given. So with that is from bilateral tolerance. So when it is in unilateral tolerance, the other part of the given unit is 0, meaning there cannot be an added variation of size in that particular limit. Let's proceed to allowances. So allowances is the difference between the two dimensions of two mating parts, the hole and the shaft, for any type of fit. It is the intentional difference between the lower limit of the hole and the higher limit of the shaft. So with just the same type of computation, we need to subtract the lower limit of the hole and the higher limit of the shaft. It is the maximum clearance or the maximum interference between parts. So maximum clearance means there is positive allowance, while when it is a negative allowance, it is called an interference. Allowance is associated with two dimensions of two parts from a fit. Here are some examples again. So the lower limit of the hole is the bottom part, and the upper limit of the shaft is at the top. So the allowance is the space between them. So here are the differences between tolerance and allowance. So in tolerance, it is the permissible variation in dimension of a part, hole, or shaft. So in tolerance, it is only one part of a machine, while in allowance, it is the prescribed difference between the dimensions of two mating parts, hole and the shaft. So in allowance, it is between two parts. Note that the tolerance, it is the solid dimensions, while allowance, we are talking about the space between the two mating parts. So it is the difference between lower and higher limits of the dimension of a part, while in allowance, it is the intentional difference between the lower limit of the hole and higher limit of the shaft. Just like I said, the tolerance is in a single part, while the allowance is between two parts. Tolerance is to be provided on a dimension of the part, as it is not possible to make an exact specified dimension, meaning that it is the provided range of a part that it may vary, while the allowance is provided on the dimension of mating parts to obtain the required type of fit. Tolerance has an absolute value without a sign. So, um, meaning that it cannot be a negative since there is no negative value for um, length or sizes, while allowance may be positive or negative, the clearance and interference.
Let's proceed to variable stress. So in understanding stress concentration, whenever a machine component undergoes a sudden change in its cross-section, the uniform stress distribution is disrupted. This irregularly leads to a localized increase in stress, which we call stress concentration. So in this figure, it shows a component that narrows in the middle, and you can see how the stress lines are bending and crowding near the transition. This illustrates how stress accumulates in areas where there are abrupt changes, such as fillet, notches, holes, keyways and splines, surface roughness, or scratches. These stress concentrations can lead to failure, especially in cyclic loading conditions, making it essential to consider in engineering design. Theoretical or form stress concentration factor. So to quantify the impact of stress concentration, we define theoretical stress concentration factor denoted as Kt. So in mathematical formula, we have Kt is equals to maximum stress over nominal stress, where maximum stress is the highest stress occurring at the discontinuity, and nominal stress is the expected stress assuming a uniform distribution. The value Kt depends on material properties and geometry. Engineers use charts and formulas to determine Kt for different shapes and loading conditions. Fatigue stress concentration factor, or K sub F. So when a machine component is subjected to cyclic or fatigue loading, the theoretical stress concentration factor alone is not enough to predict failure. So instead, we use the fatigue stress concentration factor denoted as K sub F. And for experimental test, it is mathematically defined as K sub F is equals to endurance limit without stress concentration over endurance limit with stress concentration. So this factor accounts for how repeated loading affects the material's ability to withstand stress over time. So since determining fatigue stress concentration factor precisely is difficult, it is usually obtained from experimental data. So notch sensitivity, or Q, in cyclic loading, the actual effect of a notch or fillet is often less severe than what is predicted by the theoretical stress concentration factor. And this is because of stress gradient around the notch and the material hardness influence how stress is distributed. So to quantify this behavior, the notch sensitivity factor is here, which measures how much of the theoretical stress concentration is actually realized, and it is defined as Q is equal to K sub F minus 1 over K sub T minus 1, where the K sub F is the fatigue stress concentration, while the K sub T is a theoretical stress concentration factor. So using this, we can express the fatigue stress concentration factor in terms of theoretical stress concentration factor. So for tensile or bending stress, we have K sub F is equals to 1 plus Q times K sub T minus 1. And for shear stress, we have KFS is equals to 1 plus Q times K sub TS minus 1. So the value of Q depends on the material's hardness, harder materials tend to have lower notch sensitivity, so meaning they experience more stress concentration effects. Methods of reducing stress concentration. So the figures shown illustrates different approaches to improving mechanical design and minimizing stress concentration. To better understand the figures, we have two sets of diagrams. The top set represents axial loading cases. The bottom set represents bending loading cases. Each set is categorized into poor, good, and preferred designs. In axial loading cases, we have A figure, which is the poor design. It is poor because its abrupt changes in cross-section causes high stress concentration. This design is more prone to failure. The B figure is good design because it has a smoother transition, which is used to reduce the sharp stress risers. This helps in distributing the stress more evenly. The C is preferred design because it has incorporated smooth curves and fillets, reducing likelihood of stress accumulation. Additional grooves as seen in figure D further aid in stress distribution, such as keyways and notches. In bending loading cases, we have figure A. The figure A is poor design because it has sudden transitions in the cross section, create weak points. High bending moments lead to concentrated stresses at these points. Figure B is good design because it is gradual transitions and fillet helps in reduce stress, and it is still not optimal, but it is significantly better than figure A. And in figure C, the figure C is preferred design because this is a well-rounded, smooth transition with additional features to further distribute stresses. This is the best design choice for reducing failure risk under bending loads. Now let's proceed to the sample problem. So the first problem states that the piston rod of a steam engine is 50 millimeter in diameter and 600 millimeter long. In the diameter of the piston is 400 millimeter and the maximum steam pressure is 0.9 Newton per square millimeter. Find the compression of the piston rod if the Young's modulus for the material of the piston rod is 210 kilonewton per square millimeter. So the given are 50 millimeters for piston rod diameter. For the length of piston rod, we have 600 millimeter. Piston diameter is 400 millimeter. Maximum steam pressure is 0.9 Newton per square millimeter. And Young's modulus is 210 kilonewton per square millimeter. So the first step is to calculate the cross-sectional area of the piston. So the formula for cross-sectional area is A is equals to pi over 4 times d squared. So we can substitute the diameter of the piston. So we have pi over 4 times 400 squared. And the answer will be 125,680 square millimeter. So step 2 is to determine the maximum load acting on the piston due to the steam pressure. So we have the formula of P is equals to cross-sectional area times the steam pressure. So substitute the values. We have 125 1,680 square millimeter times the maximum steam pressure value, which is 0.9 Newton per square millimeter. And the answer will be 113,110 Newton. The step 3 is to compute the cross-sectional area of the piston rod. So again, we will use the cross-sectional area formula, which is the pi over 4 times diameter squared. So we will substitute the piston rod diameter. So we will have pi over 4 times 50 squared. And the answer will be 1,964 square millimeter. Now the step 4 is to apply the Young's modulus formula to find the compression. So the Young's modulus equation is E is equals to P times L over A times the compression. So we will equate the compression, and we will now have the formula of compression is equals to P times length over E times A, or the area. So substitute the values. We have 113,110 times 600 over 210 times 10 to the third times 1,964. And the answer will be 0.165 millimeters. So the next problem, determine the thickness of a 120 millimeter wide uniform plate for safe continuous operation. If the plate is to be subjected to a tensile load that has a maximum value of 250 kilonewton and the minimum value of 100 kilonewton. The properties of the plate material are as follows. Endurance limit stress is equals to 225 megapascals and yield point stress is 300 megapascals. The factor of safety based on the yield point may be taken as 1.5. In given data, we have plate width, which is 120 millimeters, the maximum load of 250 kilonewton, minimum load of 100 kilonewton, endurance limit stress of 225 megapascals, yield point stress is 300 megapascals, factor of safety is 1.5, and the problem here is to determine the thickness of plate. So we have the step 1, which is to calculate the mean load. So we have the formula of mean load, which is W max plus W minimum all over 2. So we will substitute the value of load, maximum load and minimum load. So we have 250 plus 100 over 2 is equals to 175 kilonewton. The second step is to compute for the mean stress. So the formula for the mean stress is sigma sub m is equals to mean load over area. So substitute the value. We will have 75 kilonewton over 120 T Newton per square millimeter. So the step 5 is to apply the Sodenberg's formula. So we have the formula of 1 over FOS, or factor of safety, is equals to omega M over omega B plus omega V over omega C. So substitute the values. We have 1 all over 1.5 is equals to 175 kilonewton over 120T times 300 plus 75 kilonewton over 120T times 225. So we can shift solve this one to find the required thickness of the plate. And the answer will be 11.46. And if we round it off, we will have the final answer, which is the 11.5 millimeters. So the required thickness of the plate for safe continuous operation is 11.5 millimeters.
Materials and their properties. Materials and their properties. The knowledge of materials and their properties is of great significance for a design engineer. The machine elements should be made of such a material which has properties suitable for conditions of operation. In addition to this, a design engineer must be familiar with the effects which the manufacturing processes and heat treatment have on the properties of materials. So we have classification of engineering materials. One is metals and alloys. So metals and alloys, we have the iron, steel, copper, aluminum. Yun yung mga usual na ginagamit sa materials. Sa non-metals, glass, rubber, plastics. Yan. Sabay sa metals, further classified into ferrous metals naman. They contain iron, cast iron, wrought iron. Basta anything with iron is classified as ferrous metals. So we have selection of materials for engineering purposes based on availability, working conditions, and cost. Kailangan din natin i-consider yung kanilang physical, chemical, and mechanical properties. So sa first, we have availability. Refers to the ease of sourcing the material in the required quantity and quality. So dito sa availability, kailangan natin consider kung saan pwede siya mabilin, yung kanyang supply, and also lead times for procurement. So that means the total time it takes from the moment a purchase order is placed with a supplier until it is delivered. So ayun. Next is our working conditions. Encompasses the environment in which the material will be used. So dito ini-include yung temperature extremes, corrosive atmosphere, example is exposure to chemicals or salt water, mechanical loads and vibrations, wear and tear due to friction or abrasion. So sa ikatlo, cost, basically yung kung magkano ang isang material, expenses na magagastos mo. We have your material and material procurement cost, manufacturing and machining cost, maintenance and life cycle cost. Selection of materials for engineering purposes based on availability, working conditions, and cost. We have one, physical properties. These properties determine how the material responds to external physical forces. So we have four. First is density. It affects weight and structural design considerations. Two is thermal conductivity, kung paano nakaka-absorb ng heat. Important for heat transfer. Electrical conductivity. Ito critical to for electronics and electrical applications. Fourth is the melting point. It determines suitability for high temperature applications. So the second is chemical properties. Define the material's resistance to chemical reactions. So we have three: corrosion resistance, oxidation resistance, reactivity. Corrosion resistance, meaning the aggressive environment like marine and chemical plants, yung nakaka-affect sa chemical properties natin. So oxidation prevents deterioration in high temperature conditions. Sa reactivity naman, compatible with other materials na na-expose to chemicals. So next we have mechanical properties of metals. First is strength. Ito ay resistance to force without breaking. So, nakakandal ito ng force. Halimbawa, naghampas ka ng hammer sa isang metal, hindi siya nag-break. Mataas ang kanyang strength. So, stiffness naman, resistance to deformation. Stiffness is when you use a hammer into a metal, it doesn't deform or change its shape. Sa elasticity, ability to return to original shape. Ang basic example nito ay elastic band o kaya elastiko. Sa plasticity naman, ability to retain deformation under force. For example, you pulled a plastic into two pieces, so mariretain yung kanyang pag-deform gamit yung force na nailagay mo. So sa ductility, ability to be drawn into wire. Basically, it's the ability to stretch or bend without breaking. Brittleness naman, tendency to break without deformation. Means you can break it into little parts. Sa toughness, resistance to impact loads. Kung gaano nyo na-handle yung impact ng loads, that's how tough the material is. Second is hardness, resistance to wear, scratching and deformation. So it's also like stiffness, but here resistance to wear and scratching. Sa creep, slow deformation under stress over time. Basic example is mga timing belt sa sasakyan or sa motor. Wear and tear, slow wear and tear. Sa fatigue naman, failure under repeated stress. So, machinability refers to a relative case in which a material can be cut. That's it. Resilience, ability of a material to absorb energy and to resist shock and impact loads. So this is like the same with toughness, but it absorbs the energy. Sa malleability, permits materials to be rolled or hammered into thin sheets. It's a metal, but it can be rolled or hammered just like parang yero. Sa ferrous metals, these are metals that contains iron. So cast iron, brittle but strong in compression, used in machine bases, pipes, and gears. Sa wrought iron, this is tough, malleable, used in chains, hooks, and railway couplings. Next is steel, an alloy of iron and carbon classified as mild, medium, and high carbon steel. So we know what steel is. We can find it kitchen, hardware, anything with stainless steel. Sabay, types of cast iron. We have 4. First is gray cast iron, good machinability. So it can be for cutting, used in engine blocks. Can be cut. White cast iron, hard, wear resistant, used in crushing equipment. So ito yung pwede pang testing, like testing machines that presses onto other metals for crushing. So nodular also ductile cast iron, high strength, used in automotive parts. So that is what we use. Alloy cast iron contains nickel, chromium for wear, and corrosion resistance. So, effect of impurities in cast iron and steel. We have three: the silicon, the sulfur, and phosphorus. So silicon, it improves the machinability. Sa sulfur, the brittleness. Sa manganese, improves hardness. Phosphorus increases strength but reduces toughness. We have next the alloy steels and their properties. We have 5. Nickel increases strength and toughness. Chromium enhances hardness and corrosion resistance. So tungsten improves high temperature hardness. Vanadium increases strength and fine grain structure. So molybdenum, it improves the tensile strength or the tension strength.